Okay, perfect. Well, welcome everyone. We're pretty excited to have this parallel session on mechanistic modeling under future climates. This is one of the two sessions from the core modeling program in Global Water Futures to showcase some of the recent progress that we've been making over the past couple of years. As a quick background, as we remember from John Pomeroy's talk yesterday, Global Water Futures is seeking solutions to water threats in an era of global change. The goals are twofold: to place Canada as a global leader in water science for cold regions, and second, to address the strategic needs of the Canadian economy in adapting to change and managing the risks of uncertain water futures and extreme events. In the core modeling program, it's led by Al Petronero and myself. Al Petronero will be chairing the second core modeling session tomorrow. And we've got the very able core modeling coordinator, Prabin Rakaya, who is co-chairing this session with me today. The research themes that we have in core modeling are spatial meteorological forcing data, chaired by Julie Theroux, geospatial intelligence, chaired by myself, current generation hydrological modeling, chaired by Bruce Davison, next generation hydrological modeling, chaired by John Pomeroy, water quality modeling, chaired by Philippe Van Capellen, water resources modeling, chaired by Trish Stadnick, hydroeconomics by Roy Brower, and hydrological forecasting by Al Petronero. We've got 31 faculty, 33 research personnel, primarily postdocs, and 21 collaborators. Associated with core modeling, which we'll touch on a little bit in the session today, is the Global Water Futures Planetary Water Prediction Initiative. That initiative has got two goals. One is to build the computational infrastructure, models and data to enable state-of-the-art hydrological simulations anywhere on the planet. And the second goal is to develop regional models in key areas where GWF has strong collaborations, primarily in areas dominated by cold regions hydrology, the Arctic, Himalaya, Andes, Central Asia, etc. So with that, I'll pass off to our first speaker. And I've just lost my notes here.
Our first speaker for today is Fuad Yassin, who will be talking about water balance analysis of the Saskatchewan River Basin.
Okay, thanks, Praveen.
Fuad, the floor is yours.
Thank you, Praveen and Martin. All right, thanks everyone, and sorry for this disruption with the screen sharing. So yeah, I'm happy to start this session with my presentation on hydrological modeling of Saskatchewan River Basin. And as shown here, I would like to acknowledge my co-authors for this work. And in my research work, we are in the process to address the following research questions using a mesh hydrological model, that is how much stream flow is generated in the mountains and prairies and boreal forest, how much stream flow is generated by glacier melt, snow melt, rain on snow, rainfall runoff process, and check how the water body component respond to drought and very wet years, as well as how much irrigation consumption is occurring in the basin and how that varies over time and space. So to enable mesh, we added important process, including glaciers, blowing snow, transport and sublimation, reservoir operation, irrigation, and non-contributing area dynamics. And we built the hydrological model using a wide range of data explaining topography, river network, land cover, soil type, and meteorological forcing. We configured the model setup at 10 by 10 kilometer grid scale and derived the model with GM kappa forcing. And the model is used to simulate different variables across watershed over time, including evaporation and runoff. So such hydrological results are becoming very important because of the global warming and climate change. And this way we assess how our water system may change under new climate conditions and how much sustained water will be available for various water demands. Within mesh, we have water coming to mesh. So we have water and PDM rough represent lateral flow simulation, and we have class to represent vertical flow and energy simulations, and wattflow to compute gridded flow routing. Irrigation diversion and reservoir model communicate with river routing and class to compute water demand, flow diversion, and release. Among the lateral flow, water algorithm is used for hill slope hydrology, while PDM is a suitable option to represent the dynamic contributing nature of the prairies. So we configured the model with a combination of water and PDM as shown here. Blowing snow is transport and sublimation is a key process in the prairies and the mountains, and the quantities are calculated within the grid square across tiles using a prairie snow model developed by McDonald 2009, and calculation order based on tile aerodynamic sequence, that is like from smooth to rough surface, from high elevation to low elevation. And so the wind eroded snow transport out from one tile and transport into the next tile, and part of it sublimates. Saskatchewan is regulated by many reservoirs, irrigation and diversion, which makes the modeling task more challenging. To model the irrigation, we first estimated the irrigation fraction by separating cropland into irrigated and non-irrigated cropland. And then soil moisture deficit irrigation algorithm is used to calculate the irrigation demand. And irrigation water can be diverted from local grid cell for irrigation tile or from downstream of a reservoir. And also to enable the reservoir operation, we incorporated a reservoir operation model in mesh by refining the existing methods and introducing dynamic characterization of reservoir storage and zones and release. And what makes this reservoir model unique is the flexibility of dynamic monthly storage and outflow parameterizations using observed reservoir inflow, storage, and discharge data. The reservoir model makes water release decision at each time step using a piecewise linear and monotonic function using storage in and out inflow to the reservoir. Coming to Glacier, for Saskatchewan River Basin over the mountains, the glacier fraction estimated based on the Randolph Glacier inventory data, and the total area in the basin is close to 340 kilometers square, and majority of the glaciers is located on the northern Saskatchewan and Bow, and some portion located in the Oldman Basin. In mesh, we represent glacier as one-dimensional ice, so the glacier can grow depending on some threshold set on conversion to convert snow to ice, and it can lose also mass by ice melt. So I'm showing here the glacier mass balance result for each hydrological year over the simulation period from 2005-6 up to 2015-16. All glacier showed negative mass balance, which means extra flow is coming from the glacier ice melt, resulting glacier retreat. And more negative water balance is estimated for southern part. That ranges between around 1,000 and somewhere 3,000 millimeter. And on the other hand, the northern glaciers over the North Saskatchewan and Bow they showed they lose glacier at a low rate, ranging from a couple of -100 to a couple of -1000s. So as a validation, so far we managed to validate some result for for the northern part using Pito Glacier mass balance observation. Blue is observed and red is mesh result. So overall, as you can see here, the overall inter-annual pattern is followed. For some years, we can see very comparable results, but in the middle, mesh tends to overestimate. But this is, we found it very encouraging because we don't see often land surface models produce such results for glaciers. And also it's important to account several factors placed to this affect the annual mass balance and the glacier energetics, such as the bias on solid precipitation, snow ice conversion parameters, glacier albedo values can affect this result. So we are in the process of validating the southern part using glaciers in Montana. And here I'm showing the annual average spatial precipitation plot, and the majority of the precipitation is over mountainous region and much lower value for the rest of the basin. Here I'm showing the precipitation phase for long-term annual average, and the precipitation dominantly occur as snow over the mountains and the foothills, and in the flat terrain is dominantly occur as rain. And climate change expected to create more rain phase, and which will affect the runoff generation mechanism in the basin. So here is the graded annual average water balance output for runoff and evapotranspiration. Runoff is dominantly contributed from mountainous, followed by the foothills, and then some portion from the prairies. It is follows similar pattern as the precipitation. On the other hand, evapotranspiration is dominated over the flat terrain of the prairie region, and the prairie region high water holding capacity, flat terrain, and the presence of many wetlands contributes for higher evapotranspiration. Overall, our plan is to have a similar output for this historical and also produce for the future period, so that we can identify water balance change due to climate change and increasing water consumption. So and our additional target is to partition the runoff into based on the source snow melt, rainfall runoff, and rain on snow events. So far, we estimated the frequency. Here, the plot shows the runoff generation number of events per year, averaged over 2006 to 2016. We used literature value to identify what is snow melt runoff and rain on snow and rainfall runoff. And for mountainous, dominantly, like for most runoff events, mainly due to snow melt, freshet over the mountains, followed by rainfall runoff event in the summer over the foothills and the prairies. And the remaining is from few rain on snow events, but they are important because rain on snow cause floods in the basin, and they can become more frequent with changing climate, resulting a shift from snowfall to rain, particularly where we still have on snow cover or where snow cover persists. So with this suggested parameterization, the prairie tends to have low events. So we also tested changing those values, and we see that there's a possibility we are like identifying the suitable threshold to partition this, so that we will partition the runoff to each cause. This is a result to show how well the uncalibrated mesh model simulates at daily time scale for main subbasins. The performance is summarized using Klein-Gupta efficiency performance metrics. The first 2004 and 2005 is taken as a warm-up period. and the clean Gupta matrix varies from 0.45 to 0.71. And the lowest is for the Battle River near Saskatchewan boundary, and the remaining showed almost greater than 0.6 values can be taken as a good simulation. Please note that this is uncalibrated model runs with basically we can say default parameterization. We expect improvement with parameterizing some selected parameters. So these are ongoing work before switching to climate change and irrigation expansion simulation. So we will conduct calibration of selected conceptual parameters, verify water budget component states and flux, glacier water balance check for the southern glaciers, comparing simulated SWE against observation at multiple locations, sub-basin scale water balance analysis, irrigation output with validation, and more importantly, producing the future climate and land use hydrology water resource simulations. And with that, I would like to say thank you, and if you have any questions, let me know, please.
Okay, perfect. Thanks, Fuad. That was excellent. We don't really have any time for questions right now, so there may be some time for discussion at the end of the session. So we can move on to the next presentation, who will be Mohammed, talking about advances in permafrost modeling. So Mohammed, if you can take it away, that would be fantastic.
Thanks, Martin. Let me share my screen. Right, so everything is set, I hope.
Yep, it's perfect.
All right, so let me start by acknowledging the contribution of my co-authors here. And the map in the background shows the widespread extents of permafrost in Canada, which taken from the Canadian Atlas. So we have most of the country underlain by permafrost in one way, one class or another, more continuous towards the north and less continuous in the south. And so that leads to that we have to consider permafrost in our modeling of the basins in the northern part of Canada mostly, because there are massive implications for the hydrology and infrastructure, and more importantly, like the storage of carbon within this permafrost that can be released and that can have a positive feedback on the climate change itself, with the permafrost too that can come up due to the rising temperatures. In terms of modeling, the permafrost modeling requires deep soil profiles, and so that we can capture the dynamics of the active layers at the top of the permafrost, and the heat storage underneath that layer, as shown in the schematic and on the left, on the right. Then this causes an issue with the large thermal and hydraulic memory of the system that makes it difficult to initialize. The depiction on the right shows normal like temperature envelopes in the far north, but where like the active layer thickness is mainly defined by the thaw depth. But sometimes we get also further south more complicated envelopes where the active layer thickness could be decreasing, but the total thickness of the supra permafrost, the layer above the permafrost, where is increasing, and there is could be formation of tilex that change the connectivity of the water movement in the soil, and then those areas are also have shallow permafrost, so you can reach the base of the permafrost within the soil profile that you are modeling. So we took an approach to try to initialize the mesh model using for permafrost, and this map shows the scarcity of the sites. You can see here, like the permafrost observations are concentrated along the Mackenzie Valley here, some in the Delta. The Mackenzie is my main focus area, and then on the Yukon-Alaska highway. And then there are vast areas where we don't have observations. And then yet we want to use the modeling, validate the model using the available observations, and then generalize it to use it in prediction mode in areas where we don't have observations. I think if I give enough background on the mesh framework and the different components of the model there, so I will focus on the changes that we made to accommodate for permafrost. First, we increased the soil profile from the usual 4-meter thing, 3 layers, to use 50 plus 50 meters or more, and with deep, like 25 layers. We had to include organic soils specifically, and we increased the flexibility of the model to to configure the organic soils, because they are important in insulating the permafrost. The study focuses on 3 sites in the different permafrost zones here, one in the sporadic zone, one in the discontinuous permafrost zone, and one in the continuous permafrost zone, so that we can see what is common and what can be generalized to other areas where we don't have enough observations. And it is the organic soil map, and we see a lot of organic soils in the Mackenzie Valley, which are very important in maintaining the permafrost and insulating it in winter and summer alike. In winter, we have the extra insulation from snow, but in organic soils work all year round. The main question that we had to answer here, how deep to consider organic soils, while we didn't have enough information in the soil database that we used. In those areas we selected, we had soil logs, so we could know how deep the organic soil is. But in other areas, we had to improvise and find some general formula so that we can take the soil data forward. So we started looking at initialization methods. So the simplest one is use 1 year of climate data and keep running the model back-to-back cycles until it reaches some stability. Other methods like spinning, you can spin with a sequence of years, and then you get into the problem of having a trend in those years. Then you can do detrending and then add the trend, but then you add a layer of uncertainty with this. The other thing is you start your simulation from using paleoclimatic records like 300-400 years ago, and then assume at that point in time or that you have some stability in the climate, or you have also to use spinning so that you reach some stability. And we found out that not only like the climate affects this, but also the soil layering affects this. So these are two soil layering schemes with they differ in the thickness of each soil layer, but they reach almost the same depth. But this one reaches stability much faster than this one. So that the soil discretization, vertical soil discretization is a critical element of how to initialize the model. The second thing is,
Hi, Mohammed, can you begin to wrap up your presentation?
Yeah.
Thanks.
So we went with spinning a single year, and we took a pragmatic approach to see whether if we spin less, how much the results are affected. And we found like we don't have to spin thousands of cycles. We could spin like 100 or 50 cycles, and the differences in results in terms of active layer thickness and in terms of temperature profiles are manageable. And these show how sensitive is the model also to certain important parameters like the depth to the bedrock and the organic thickness. And we could manage to get the profiles in some areas very nicely. In some areas, the cold envelope was a little bit overestimated, like colder than usual. And this can be the effect of the quality of snow simulation or the quality of modeling the organic soils. This work is extended by Mohammed Abdul Hamid and looking at the ice content of the soil in the initial conditions. And there is a poster on that on tomorrow poster session. I would like to invite you to look at it. So to wrap up, then we can say like using the extended soil profile and the initialization methods that we used, the mesh is suited to simulate the permafrost dynamics. And with proper initialization, we can get reasonable performance. The quality of the snowpack simulation, we are still assessing that now to further improve the results, and then we can go forward in the future and look at how the impact of the climate change on permafrost looks like. And with the current model, we can actually detect the formation of talics, as I mentioned in the beginning, and we can look at impacts on the horizontal connectivity between the elements. And with that, I would like to thank you and have any questions.
Thanks, Mohammed. That was very fantastic. I don't see any questions now, and we're also running out of time. So I would like to move to the next presentation. Next, we have Yangping Lee. She'll be presenting on regional climate modeling and future climate projections for Western Canada. Yangping, the floor is yours.
Okay. Can you see my screen?
Yep, it's perfect.
Okay, good. So, hello everyone. I'm Yangping Lee, the lead of the high-resolution WRF regional climate simulation for GWF modeling. So today I would like to update the status of the CONUS-2 simulation, which is also a joint effort of between NCA, the Research Application Lab, the NCA team led by Roy Rasmussen, and including others like Changhai Liu and Kyoko Akida, and also the group at the University of Saskatchewan, led by me, and including Ling Tao Li, Zhenhua Li, Lucia Scaff, and Zhe Zhang. So This is the new 4-kilometer WRF CONUS 2 simulation, which has a much larger domain that covers almost the whole US, continental US, and Canada. And this domain almost double the size of the CONUS 1 simulation. The model setup includes some new features in addition to the new version that we used, the new WRF version that we used, also with additional vertical layers. Now it's 51 vertical layers. The cloud fraction we used is Xu Randall and the Thomason scheme. And the model also include a new groundwater scheme with the saturated aquifer added to the bottom layer. This new CONUS 2 simulation is 20 years from 1995 to 2015. For the new CONUS 2 simulation, the 4-kilometer WRF is forced by the synoptical scale perturbation provided by NCA GCM model, the CCSM model, or we use CCSM prime here, plus the climate average derived from ER interim, the 30-year average. So this is the historical simulation. For the future climate simulation, we know that I think you probably already heard that the CONUS 1 used a method that is called the PGW, or pseudo-global warming. This approach was used to get the climate change information at the regional scale instead of doing the central long dynamic downscaling. This allows us to increase the domain, the size of the domain to a size that is comparable to the continental scale, but still keep the file resolution and with the regional amount of computational cost. So for CONUS 2, future, it is a similar method, but for the future climate simulation, it is forced by a single GCM, the NCA CCSM, and instead of the simplified GCM ensembles. So the impact of the change of the storm track position can be included in the future climate simulation, for which the CONUS 1 PGW simulation do not have. So during the meantime, we also conducted the 12-kilometer WRF CONUS 2 simulation, the historical and the future simulation, which is the purpose is to evaluate the added value of the high resolution WRF simulation. So the 4-kilometer and 12-kilometer WRF historical simulation was completed. And we are currently working on the CONUS 2 future climate simulation. The detailed work for the future simulation include testing of different forcing setups, such as like sea ice, lake ice, for the future climate simulation. And we have also conducted some preliminary analysis during the meantime to evaluate the CONUS 2 simulated temperature and precipitation over Canada for the 20-year period from 1995 to 2015. So we have produced the post-processed files for CONUS 2 historical simulation, which include both 4-kilometer and 12-kilometer simulation. So here is a list of the variables that we have archived, which include the hourly data for 2D surface data and the 3 hourly, that's 3D for 3D data. We also have daily and monthly variables available that we have archived. So the data is stored in Computer Canada together with the CONUS 1 and the Western Canada WRF 4-kilometer WRF simulation that we have conducted. It's a huge amount of data, but to put it in Computer Canada can can make it easily accessed for the GWF community. So here I would like to show some preliminary results of the CONUS-2 historical simulation. So what I showed here is the CONUS-2 simulated temperature compared with the WRF DEI reanalysis. So it's for different seasons, and the reanalysis data and the WRF simulation and the differences. Just by look at the rough results here, it seems that the CONUS-2 WRF simulation capture the main spatial and the seasonal features of the reanalysis data. The large cold bias during the spring, and remember, I didn't show it here, but just if you have heard our previous talk about CONUS-1 and the West Canada simulation, we had some large cold bias in spring season over the Canadian prairies in the CONUS-1 and the Western Canada simulation, but it is much less or much attenuated from about 4 kilometers. Oh, sorry, from about like right now it's more like a 1 to 2 degrees C, and in the past it can be up to 4 or 5 degrees C. So this is the spring, this case in spring, and there still exists some relatively large warm bias in the north region in spring. I mean, okay, you can see it here, and cold bias through the whole domain during the winter. This is the cold bias. Summer and the fall, the autumn bias are relatively small with warm bias on the west and the cold bias in the east, but the magnitude is relatively small. So this is the temperature. As to the precipitation, so what I showed here is the CONUS-2 simulated precipitation compared with kappa. So CONUS-2 captures the main characteristics of the precipitation distribution compared with kappa. So the patterns are very similar, but there's also still exists some significant wide bias in southeastern US, southeast US in summer, and wide bias along the coastal regions of BC. For all these seasons, you can see it here. This is a quite significant features.
Hi, Yanping, can you begin to wrap up?
Okay, sorry, yeah, I'm almost done. So the model, so I should say the model does a pretty good job for Western Canada, especially for the prairies. That's the region we are interested in. So this is my last slide. So this is the 20-year average annual cycle for temperature and precipitation for Saskatchewan River Basin and the Mackenzie River Basin. So in general, the model captures the main annual cycle of temperature in both basins. The main problem is the cold bias in winter in both regions. So we still have cold bias, but the warm bias is very small for like in summertime in Saskatchewan River Basin and in spring in Mackenzie River Basin. And the precipitation annual cycle, WRF actually underestimated precipitation in both regions. In both regions, in summertime and in autumn, and also a small wide bias in spring, and dry bias in March in Saskatchewan River Basin. So this is the end of my talk, and thank you.
Thank you, Yankin. That was very interesting. So we have one question, and I think because of the time, you can answer the questions by typing the answer. So, and also
okay, I'll do that.
If you have any questions for any of the previous speaker, you can still type in the question and the speaker will write in the answers. For now, we're moving to the next speaker. Next, we have Gochang Tang, who will be talking about EMR, the Ensemble Meteorological Dataset for Planet Earth. Gochang, the floor is yours.
Hello, everyone. Can you see my slide well?
Yes.
Okay, good. Thank you. And I'm Gochang Tang, and today I'm glad to introduce our latest meteorological dataset to you. The name is the Ensemble Meteorological Dataset for Planet Earth, and we will call it EM Earth in this presentation. And the motivation is the limitations of the current measurements and models. So our meteorological data are from ground stations, from remote sensing, or from numerical models. But all those sources contain uncertainties or errors. For example, the ground stations are at the point scale, and the interpolation of station data will introduce uncertainties. And station data have limited coverage and also measurement errors such as undercatch of precipitation. The remote sensing techniques are popular recently, but the remote sensing techniques also have limited coverage and retrieval uncertainties or short periods. And the numerical models, of course, it has imperfect representations, observational trends, and many other factors. So far, we have numerous regional or global deterministic datasets. But those datasets, we know they have uncertainties, and those uncertainties will affect our applications. But very few datasets provide uncertainty estimates or the ensemble estimation. So that's a goal of our work. We want to provide the ensemble probabilistic estimates so that the users can better characterize their uncertainties in their applications. This slide shows an example of the EM Earth. So the left figure shows the precipitation distribution of ERA5 data and the station data. And on the right side is our EM Earth ensemble precipitation. So EM Earth have 25 members. Overall, the spatial distributions are similar, but the details, spatial details are different. So those differences will enable diverse applications. This is the framework of EM Earth. So here's some basic information. The dataset is from 1950 to 2019, and it is at the hourly and daily scale and the 0.1 degree resolution. The variables include precipitation, mean temperature, daily temperature range, and dew point temperature. So users can infer minimum and maximum temperature from mean temperature and temperature range. And the humidity variables can also be inferred from the dew point temperature. We provide two types of datasets, the deterministic estimates and the probabilistic estimates. And the right figure shows the overall flow chart. So the basic inputs are raw station data and raw ERA5 data. Because raw station data contain temporal discontinuity, so we first produce a serially complete Earth dataset. We call it SC Earth. This is a station-based dataset, it doesn't have any temporal discontinuity. And we also process the ERA5 data to meet the temporal and spatial requirement of our dataset. And then we merge the SC Earth and ERA5 to obtain the EM Earth deterministic estimates. So in this step, we have both the values and the uncertainties of the values. And based on the values and uncertainties, we can define the probability distribution of a variable. And then we can sample from the distribution to obtain the probabilistic estimates, and which has 25 ensemble members. And then is the evaluation and the post-processing steps. Finally, we will release the dataset on open access website such as the FRDR, and so everyone can download it. Now the paper is still under review, so we don't release it yet. But if you are interested in this dataset, you can contact me, and the dataset is stored in Compute Canada, so it will be easy to share with anybody. This table shows the data sources used by EM Earth. We have two major inputs, SC Earth and ERA5. We have some auxiliary datasets, validation datasets, and 3 datasets for intercomparison. They are CRUTS, GPCC, and the UDEL. So first, I'd like to introduce the SC Earth. As I have mentioned, this is a station dataset, and it doesn't have any temporal discontinuity. We have filled the missing values using multiple strategies such as quantum mapping, interpolation, and machine learning, and multi-strategy merging. And the paper has been accepted, and we will release this dataset very soon. And if you are interested, you can also contact me, and we can share it very quickly. And this dataset, since it doesn't have any temporal discontinuity, the station density is higher than many publicly available datasets. And it has 5 variables. Also, the wind, in addition to the 4 variables I just introduced, it also have wind speed. But wind speed has some notable inhomogeneities, so we don't include this variable in EM Earth for now. And this slide shows an example of SC Earth. We can just look at the left figure. The red line is the raw observation, and the green line is the gap fill data. So we fill the gap.
Hi, Go-Chung. Can you begin to wrap up? Thanks.
Okay, sure. And yeah, the blue line is the gap fill data. So as you can see, we can cover the whole period. And then those are just some evaluation results. So I think they are good to wrap up. And I just want to say that the evaluation shows that our dataset has reasonable accuracy in most regions of the world. But of course, we also suffer from the station density and topography and climate. This is a probabilistic evaluation. We find that for example, in Asia, South America, and Africa, the quality for heavy precipitation is not so good. This is actually a problem for almost all data sets, and we will need to try to improve that in future development. And this is also the probabilistic evaluation, and I don't think those are quite important details for today's presentation. And this is a comparison between EM Earth and some other data sets. And as you can see, in most parts of the world, those data sets are similar, but in some, like in Greenland, the difference is relatively larger due to the sparse station networks. And this is a comparison of their climate trend. EM Earth uses ERA5, so the trend is affected more by ERA5, but overall they agree with each other, particularly for temperature. So there is summary. We developed 2 data sets, and we think this will be useful for users. And please contact me if you are interested in them. And that's all.
That was a very interesting presentation, and I think the work we are doing will contribute a lot to the Blue Water Futures Planetary Water Prediction Initiative. With that, as I said before, we will answer the questions online. So we'll be moving to the next presentation. Next, we have Sujata Budatsuki. She'll be presenting on the impacts of future climate on the hydrology of St. John River Basin. Sujata, the floor is yours.
Thank you, Praveen. So can you see the presentation slide?
Yes.
Okay. So hello everyone. Today I'm going to talk about impacts of future climate on the hydrology of San Juan River Basin in Eastern North America. So before I begin, I'd like to acknowledge my colleagues and co-authors who has contributed in this research. So as we all know that Atlantic Canada is one of the many regions in Canada which is threatened by global climate change, and impacts of future climate on hydrology, particularly in San Juan River Basin, is poorly understood, and there has only been few studies performed in this basin. So we need an appropriate water system modeling tools that can describe climate change and anthropogenic response in this watershed. So the main research objective is to benchmark model runs for the San Juan River Basin and assess the impact of future climate on its hydrology. So talking about some of the basin characteristics is the San Juan River Basin is a transboundary river basin, which with its portion in the state of Maine, which is in US, and in the provinces of Quebec and New Brunswick, which is in Canada. So the mean annual precipitation is 1100 millimeter, and the total drainage area is 55,000 square kilometer. But the model basin area is 41,000 square kilometer, as we do not have active gauge station beyond Fredericton, and also there is effect of tide from the Bay of Fundy. So for the hydrological modeling, we use MESH, which is a land model, and the details has already been given by Fuad in his presentation. So for the model setup, we set it up at a spatial resolution of 10 kilometer, and we used Merit Hydro as dam and Landsat 30 meter for North America for the land cover. And for the soil data for different depth, we use Unified North American Soil Maps. The streamflow data were taken from Water Survey of Canada, USGS, and the reservoir inflows and outflows were from New Brunswick Power. As you can see that there are many reservoirs in the mainstream, but they are all run of the river and they do not store water. So there is high correlation in inflows and outflows as well. And we did not use reservoir routine for our hydrological modeling. And we have the land cover is predominantly forest in the basin. So some of the forcing data set available for hydrological modeling in the basin are GEM-Kappa, WAF-DEI, WAF-DEI GEM-Kappa, which is bias corrected WAF-DEI using GEM-Kappa, which has a strength from low resolution of GEM-Kappa and record length from WAF-DEI. And for the future data set, we have CAN-RCM4, WAF-DEI GEM-Kappa, which is bias corrected CAN-RCM4 using WAF-DEI GEM-Kappa, and it has 15 scenarios. The comparatively new product is RDRS, which has improved precipitation forcing in the transboundary and also in the northern watershed. So here are the results from the multi-objective optimization using mesh on the two station. This is the calibration and validation for Grand Fall and Mactaquac. And I've also shown for different, using different forcing data set. And just wanted to highlight that we use same parameter and same ranges for all these forcings. And you can see that the RDRS was best RDRS gave best calibration and validation result for the basin, but as we do not have bias corrected RDRS dataset for future, we use WAF-DEI GEM-Kappa for our model evaluation, and also for future dataset we use CAN-RCM for WAF-DEI GEM-Kappa, and we have reasonable calibration and validation result using those dataset. So in order to simulate the future climatic condition, we have to know if our model is performing well in the baseline conditions. So we this is the result for the baseline baseline period, I mean 1991 to 2020. And what we found that the variability is less in the simulated flows, but the model was highly underestimating in April and May. So we wanted to know where this error was coming from, and we plotted the mean monthly averages from WAF-DI GEM kappa from the calibration and validation period, and we found that the model was underestimating in April and May, but on contrary, the RDRS captures better monthly variability on those months. And we also calibrate GEM kappa and WAF-DI and found similar mean monthly averages as what WAF-DI GEM kappa had given us. So we went on and ran with the future data set. As we cannot compare directly the historical and future, as there are error in the baseline period, so we calculated the relative difference between model simulated baseline period and model simulated future period and added the difference to the historical observed to get our estimated future flows. This method is also known as delta change method. And here are the results based on median of all the 150 ensembles, 10 from the parameter set and 15 from the different scenarios from CAN-RCM4 data. And we found that there would be increased winter flows between December and March, but decreased flows in spring and summer between April and July for both the stations. And we also wanted to, because there are high uncertainty in the meteorological forcing and also the models, so we wanted to compare the percent model error and changes in stream flow. So if the model error is less compared to changes in stream flow, then we can be more confident that the result we are getting is good. So we have higher confidence that from the winter flows is going to increase in future because the modal error is less, but we can't be more confident for the summer flows because the modal error is greater than just changes in the stream flow. So to conclude, I would just like to mention that the model metrics can be deceiving because we were getting good reasonable NS value for daily scale, but when we were comparing to mean monthly, then the model was underestimating for some months, and also the meteorological data plays significant role in model performance and also poses high uncertainty in model performance. And for this future flows for San Juan River Basin, the winter flows is going to increase. That might have implication in midwinter ice jam breakup in the San Juan River. But what our model error shows that we can be high confident that the winter flows is going to increase, but we can't be that confident in our result for the summer flows because of the model errors. I think that would be all for me. Thank you for your time, and I'd be happy to take any questions. Thank you.
Thank you, Sujata. That was a fantastic presentation. As I said before, we'll be moving to the next session. If any of the attendee has any questions, please type in your question and the speaker will answer them online. Next, we have Dr. Carl-Erik Linda-Smith, who will be talking about advances in ice jam flood forecasting. Carl, the floor is yours.
So I'm going to take it down a notch in scale. I'm going to look at the river reach scale of about 100 kilometers in length. Okay, so I'm going to look at ice jams, specifically ice jam flooding. So, and look at the Red River. This is an ice jam on the Red River in Winnipeg. Here's the flow direction is downstream. We have our accumulation of ice, which stems from upstream, which gets accumulated at this intact ice cover here. And this causes resistance to flow and backwater levels to rise and to flood in your upstream floodplains. And I just want to show you here just the mechanism of this ice jamming. So here we have an intact ice cover, and we have ice flowing downstream and accumulating at the intact ice cover front. And this will cause the water level to increase. It'll back up and increase the water level. And if you get more ice, this will then accumulate more here and increase the backwater staging, and we'll continue on. Now, this is also dependent on the location of the toe. So here's the toe of the jam. This would be the head of the jam. Here's the toe. And moving this could also change your morphology of the jam and also your backwater profile. So this is also an important boundary condition where that toe of the jam is. Empirical approaches have been used to correlate jamming behavior with hydrometeorological variables, for instance, maybe looking at threshold variables. One that is used operationally, this was developed by Joe Grunefeld from Hatch, is looking at the risk to flooding from ice jamming for a certain day of the year, and he's looking here at cumulative more on the runoff or cumulative rainfall and snow melt, which of course will be converted to runoff. That would be sort of one boundary condition here. The model that I've developed, the forecasting model, also includes as boundary conditions the volume of ice. The volume of ice is an important factor in forming the ice jam. I also alluded to the location of that ice jam toe, and in some instances the downstream water level, particularly at a lake, or for tidal conditions when this is emptying into the ocean. For forecasting, I'm not going to go in too much detail here, but we have frequency distributions of some of these boundary conditions and parameters as well, which I'm just showing the boundary conditions here. Random variable values are extracted from these distributions, and in a Monte Carlo simulation, in a framework, you can get in an ensemble of backwater level profiles, and that can then also be put into a probabilistic context with your percentiles here. This has also been implemented in a real-time operational forecasting system for the Churchill River in Labrador, where you get data feeds from gauges, but also forecasted input data and your ice cover type, also precipitation and temperature within the next 2 days. And for this is the stretch along the lower reach of the Churchill River, and where you have now forecasted flows and also your forecasted percentiles for jamming that would come up within the next 3 days. This can also be shown here as a longitudinal profile along that river. Here we have the left and right bank elevations. You can see here this is more of a lowland part here, more deltaic of that river reach. And we have our percentile profiles here. And then we also, as indicators, have 100%, 100-year and 20-year flood levels at these gauge locations. There are gaps in the forecasting system. One would be what happens with ice stemming from upstream ice jams. How does that look? Yeah, probabilistic or frequency distributions of where that ice jam toe is, some area in need of research. We also have hazard to human life in the floodplain, and also looking at ice jam flood risk, not just hazard, but also risk. All this too in context of climate change. And now for the St. John River, we're also looking at these things for midwinter. Most of the research that's been done up till now has been for spring breakup and also freeze up. But now we're also looking into the midwinter. I only have 10 minutes here. I'm only going to be able to maybe just touch on this part here, and the ice jam release waves, or JAVs. But there is a webinar on the 27th where I can address these other components as well. So I welcome you to that webinar that Pravin will give us information on that at some point. So just how does this work with this ice jam release waves? So this is very idealized, just more for pedagogical purposes. My attempt at an animation here. So we have here a ice jam here, in which we'll release, just to point out that the upstream water level is higher than the downstream water level here. And if that then releases it, there is a wave, an initial wave. It's almost like a dam breach that will travel downstream and can impact this ice jam here. It might even rearrange or disturb some of this morphology and cause an increase in your backwater levels here. This broken up ice will attenuate.
Carl, just a 2-minute warning.
Okay. Will attenuate, and it will then also can form or compound the ice jam severity here at the end. If you have a gate like you do on the Red River to divert water through the floodway, that too can also form a celerity wave here as well. And I do have data on this. So here's an ice jam here. This is just upstream of, the flow direction is upwards. So here's a jam here, but there's also a jam here in Selkirk. So jam in Winnipeg, at Lord Avenue, and at Selkirk. I just want to show this. It's actually a very good data set. Here we have a jam at Lord Avenue. Of course, upstream of the jam, it increases, and downstream it decreases. And then we have also our jam, the water level increases here also at Selkirk. And when that jam releases here at Lord Avenue, we do get a blip here from the wave that initially travels, but then we also have here the ice that accumulates on that jam. Yeah, that's from the ice. And then we also have, what I really wanted to look at too, is there is an inlet control structure here. When that gate is raised, what will be the impact of that on that jam? It didn't release it. You can see there's a blip here, but I guess there's additional flow coming into the system, which eventually released that jam, and then downstream at Breezy Point, we induced an additional ice jam. 2 more slides. I just wanted to show you the modeling. We can do this as well. Here we have with Riv Ice. I think it's one of the few models that you can actually model multiple jams. So I have here the jam at Selkirk and also here at Lord Avenue. And the next day it releases, and there's an increase in your water level profiles. And yeah.
Hi, Carl, can you wrap up, please?
Yeah.
Oh, perfect. That's awesome. Thank you.
Yeah. So we've got tools to look at the JAVs, and this was for open water. I also want to look at the JAVs when the ice, there's no ice here between here, it's just open water. But I think the JAVs are actually accentuated when there is an ice cover along here. So I want to look into that. Yeah, and the rest of the things I will talk about in next week. Yeah, and if someone's really interested in some of this stuff, you can have a look at this book that I brought out on ice jam, on ice flood forecasting. Thank you very much.
Thanks, Carl. That was very fantastic. As I said before, we'll be moving to the next session, but please send your questions using the Q&A button and we'll answer them online. Next, we have Julie Theroux, who will be talking about simulation of precipitation during near 0-degree storms. Julie, the floor is yours.
Thank you, Prabin. Can you see my slides?
Yes, perfect. Thanks.
Okay, great. Thank you. Thank you. So good afternoon, everyone. I'm very happy to be here today to talk about the simulation of precipitation during near 0-degree Celsius storms. I would like to acknowledge my collaborators and co-authors on this research activities. And how can I change? Okay, super. So the objective of the presentation today and also the research activity is to better understand precipitation formation and evolution during near 0-degree Celsius conditions, and also how they impact the environmental conditions. In particular, we investigate the mechanisms that lead to precipitation across the Continental Divide, and also we assess the impact of freezing on the environmental conditions during freezing rainstorm. So to do so, we conducted high-resolution GEM simulations over 2 different regions. So we focus on Western Canada. Can you see? Okay, so we focus on Western Canada, and we did 2 different simulations. One at the end of April and one at the end of June. And we did also another simulation over Eastern Canada in January 2017. And then I realized that I skipped my introduction because I didn't press the right button. How does it work? Okay, so maybe it's here. Yeah, okay. So that's the introduction. So yeah, so near zero conditions across Canada varies a lot, as you can see on this image. And then you will see the link with the slide that I just presented. So here you can see how the number of near zero events change between southern and northern Canada. And then near zero conditions are often associated with many types of precipitation. But what I wanted to see here is the difference between, for example, the Canadian Rockies and Eastern Canada, where the fraction of freezing rain during those conditions is much higher than over the Canadian Rockies. And these are the two regions where I'll be focusing on and looking at the precipitation formation and evolution and their impacts during near zero conditions. So as I said just before, we conducted high resolution simulations over those two regions, and I will be presenting some of those results. So the first one I wanted to show is about the storms across the Continental Divide. So what we did is we focused on two storms that were documented during the SPADE projects. And those two storms produced precipitation on the eastern side of the Canadian Rockies. So it was basically a low pressure system located over southern Alberta, Saskatchewan, near the US border, bringing easterly flow and upward motion and precipitation. So as you can see on this diagram, here is the precipitation rate for Storm 1 and Storm 2. And here on this axis is the distance across the Continental Divide. So we can see the precipitation, as I said, on the eastern side, and sometimes precipitation on the western side, sometimes not. We can see that the model captured quite nicely the precipitation, but missed the peak and snowfall here during storm number 2. So we see that storm number 1, mainly snow and no precipitation on the western side. And storm number 2, we have a mixed precipitation and rain on the other side. So we try to understand what are the differences between those two storms and what are the mechanisms or conditions leading to precipitation on the other side of the divide. So to do so, we looked at the moisture and the condensate flux crossing the divide. And here, what I wanted to show is mainly the condensate flux during those two storms. So you will see that it's two different scenarios, and that's why we chose them. So there's storm number one that is a condensate that is mainly blocked by the divide, and storm number two, where the condensate would pass across the divide. So the y-axis is pressure, and then the horizontal distance across the continental divide that you can see in yellow. And then you see the condensate flux at three different times, at times where some condensate cross the divide, so we can see it propagating to the west, but some condensate was just blocked on the eastern side of the divide. Then if we compare with storm number two, then we see this is when precipitation started to cross the continental divide. So we see condensate on the other side of the divide, and you see how it evolves. And at the same time, we see that condensate arrives near the side of the divide and then is blocked by the divide. So if we look at precip type, this is mainly snow at higher elevation. So snow or ice. So it's ice hydrometeor. When I say condensate, it includes the ice clouds and snow. And then you see also that the 0 degrees Celsius line is much higher during the second storm than the first storm. So then we expect that there is a rain-snow transition. So we see that the precipitation was crossing the divide when there's snow changing into rain on the eastern side, and also when the height of the precipitation layer is higher also than during the storm number one. So this is the first example I wanted to show you, and invite you to go see Nicolas Leroux's poster to know more about the data analysis about the SPADE project. So then if we go more to a focus problem linked to phase changes. So if we look, for example, here you see snow into rain. So when there's a change in phase, there is a change in the temperature as well. So for example, this is a vertical temperature profile. So in the previous slide.
Hello, Julie, and we have the 2-minute warning.
Okay, thank you. So in the previous slide, we saw snow changing into rain. Here we see there's a sub-freezing layer near the surface. So then we can see that if snow melts, it brings the temperature towards 0 degrees Celsius. And when it refreezes near the surface or near the melting layer, then it brings the temperature to close to 0. So those different types of conditions in near zero conditions would bring the temperature closer to 0. And this is an important process during the freezing rainstorm over Eastern Canada in January 2017, where a slow-moving low-pressure system brought a lot of freezing rain on the East Coast. So this is what was simulated by the GEM model. And then we try to understand what's the link with near-zero conditions, and we see a high occurrence of near-zero conditions with the amount of freezing rain. So to better understand that and to study those processes, we computed the amount of latent heat release, so the warming associated with freezing rain at 2 different locations. So one that was less affected by freezing rain in Moncton, and one in Miramichi, where it's more affected by freezing rain. We see the temperature evolution, we see the precipitation rate, and we see also the tendency, temperature tendency for advection and also for the latent heating. So we can see that freezing rain changed into rain, and then the freezing rain increased the temperature and contributed to help, increase the temperature to cross the 0 degrees Celsius and change into rain, even with cold advection, because it was during the beginning of the day. And then there's the implication of radiational heating. And then if we look at Miramichi, no change into freezing rain into rain, only freezing rain contributed to warm the environmental condition near the surface. The cold air and advection is competing with this warming, but won most of the time because it never changed into rain. And then there was no other factors. That's the main thing. There was no other factors contributing. So the temperature was maintained for a long time to just below 0 in Miramichi. So in summary, we are investigating the occurrence of precipitation and their impacts on the environmental conditions using high resolution simulations. It allows us to get a lot of information on the precipitation characteristics and microphysics. And then we see that there's the timing of the precipitation crossing the divide vary through storms. It depends probably on the hydrometeor melting into rain aloft, the depth of the precipitation layer as well, and those factors can impact what the amount will be the amount of precipitation crossing the divide. And also those precipitation can interact with the environment. And then, for example, the freezing can contribute to eliminate freezing rain and bring the temperature to equal to 0. And then if you have another factor contributing to the warming, then it would increase it to above 0. And the latent heat of warming can also maintain the temperature to really close to 0, but still below 0 to maintain freezing rain conditions. So we continue doing some analysis on the clouds and precipitation characteristic aloft to better understand their occurrences and how they're formed and interact with the environment when it's close to 0. Thank you very much.
Thank you, Julie. That was terrific. The final talk for today is from Tris Statnik, and she'll be giving a talk on the impacts of climate change and water management on hydrological projections. Tris, the floor is yours.
Thank you, Praveen. Just sharing the screen there. Can everybody see the slides?
It's coming. Yeah,
it's perfect.
Yes, it's there. Hopefully. Okay. I'm very pleased to join everybody today from where the Bow and the Elbow River meet, which in traditional Blackfoot is known as the place of Mokinstis, otherwise known as the city of Calgary today. What I'm going to be talking to you about today is some of our height modeling at the continental scale and the endeavors that we are working to embed water resource management rules into that, and some of our future projections, and then a little bit on uncertainty and how we account for it. So the height model, for those that aren't familiar, is known as the Hydrological Predictions for the Environment model. It is a model developed by the Swedish Hydrologic and Meteorological and Hydrologic Institute. It's a semi-distributed sub-basin model that includes descriptions of land cover and soils, so it's discretized in that sense. It also has descriptions of lakes, wetlands, tile drainage for agriculture, cold regions processes. It even has water quality and sediment modules, which some other folks in GWF are exploring. And some of the future developments that our team is working with SMHI to develop are improved frozen soils capabilities. You can check out Ajay Bajrakaria's poster, one of my PhD students, water temperature, river ice, and isotope enabled. This is the domain that my group has worked with SMHI to now cover with the height model. So most of Canada, we're currently working on including the Fraser River Basin. That's being developed this summer. And in addition to that, we have the entire Pan-Arctic domain as well. So this is a very extensive application of the model. In terms of the influence of regulation, human regulation in Canada, there's a significant amount of interference on the landscape as a result of regulation. This alters the natural pathway and the travel time of the water. And so we've worked to incorporate regulation in about 1/3 of Canada, and we're working to expand that. We have looked at lakes, wetlands, and reservoirs, diversions and dams, including irrigation, as well as infrastructure operation rules. And then coupled with some work that is now posted for comment on in the Journal of Climate Change, I've worked with Stefan Deary's group to introduce a new metric that tracks the degree of regulation. And we have applied this across North America for both American and Canadian rivers. The higher the weekly hydro peaking index, or WHI, is, so these brownish gold colors, then the higher the degree of weekly cyclicity, and then the lower is more nival dominated or on an annual scale. And so you can see that a lot of our large Canadian rivers behave more snowmelt dominated, which isn't a big surprise. So in terms of some of the work to embed regulation into HYPE, we have developed a model that basically introduces different operational functions. 1 or 2 outlets are possible. Different operating zones are generated from the drought zone up to the flood zone, with operation target levels in between. And when we introduce this kind of simulation capacity into the model, you can see that we significantly improve the representation of observed data, which is shown in black, over the model without, which is the green one. So whereas the traditional green one would be kind of an estimate on average, the red line, which is with the regulation, comes much closer to actually simulating the observed model. This is important because this model uses publicly available data only, so it is generally accessible in regions of sparse data inputs. Within the core modeling team, we're also expanding this capability. I'm showing a simulation from Shervan here that is work to embed some of the the water management rules into network-based routing. To look at lakes and reservoirs, but also water management rules themselves. We're also working on integrated water resource management modeling for decision-based scenarios and accounting for management rules and operations within cold regions. So looking at ice-affected rating curves as well. There's a lot more description on the website of what we're doing, and you guys can keep up with that and certainly email me if you have any questions. In terms of the projections for the future, I'm just showing here some of our Hudson Bay projections, but generally speaking, we know that it's getting warmer by about 1 to 2 degrees Celsius by the 2030s and 2.5 to 5 degrees Celsius by the end of 2070. And with that warming is also coming a wetter climate. It's much more variable, less wet in the interior or the Canadian prairies, and more wet as you move towards the north. So what does that mean? Well, there's a lot of uncertainty when we translate, or a lot of non-linearity when we translate climate change into water projection or water supply. But generally speaking, we do see that there's going to be more water on the landscape, except for some regions where the trade-off between increasing precipitation temperature and evapotranspiration is much more significant. And that happens across the inflow limited prairie region. So we're using the modeling to identify some hotspots and to look at longer term periods and future projections, particularly across the prairie region. We're also looking at this from a lens with and without regulation. You see here the regulated scenarios over time in terms of discharge, as well as the renaturalized, which is where we take the model and pull the regulation out. And the thing to note here, this third panel represents the differences between the two, is that the differences happen less so during the peak flow and more so on the shoulder season. So that's where we kind of have to be careful and look at the uncertainty in these projections and what's really changing on the landscape and how regulation is influencing those time periods. So on that note, we're also really concerned with uncertainty and how to describe that through the modeling chain. As we saw, particularly over the prairies, there's a lot of uncertainty in these projections, and it needs to be accounted for. And the way that our team uses or accounts for that is by using ensembles, which you can see here in the animation for the Saskatchewan River Basin. And we use those ensembles to describe the uncertainty due to inputs, model structure, the parameters, the output data, as well as the future water management or regulation rules. Sorry, it's just slow to change because of the animation. There we go. But much of Canada is ungauged. So my team has most recently been working on ways to transfer uncertainty from gauge regions where we have a lot more information on all of those kinds of uncertainties to ungauged regions using a method that basically correlates the antecedent precipitation index to the average monthly flow or discharge. Unlike previous regionalization methods, this method is really looking at transferring based on variability of basins and similarity between basins based on variability of the flow. And we've had a lot of success with this. So up here, you see we've done an extensive uncertainty analysis, which has given us these 10th and 90th percentile bounds in dashed lines around the mean flow. And when we pretended like we didn't have that information and applied this method, we were actually able to recreate those with a fair degree of accuracy. Similarly, within the Great Lakes region, these are just a few gauges that I've shown. And even more surprisingly, when we transferred the uncertainty from the Nelson River Basin as donor basins to the Great Lakes region, which is entirely different physiography altogether, we were also able to reasonably recreate the uncertainty in many cases. So future directions, I guess just to point out that our group is using Ensemble methods, not only to look at input data uncertainty, but also modeling uncertainty. So we drive ensembles with ensembles. This allows us to create a critical evaluation of reliability of the model projections. We're also looking at water management modeling because we believe it's critical for the accurate projections. This includes network-based routing at global and continental scales, as well as the integration of regulation rules at the land surface and hydrology scale. And really the next steps are to focus on the irrigation withdrawals. And last but not least, certainly still considering the differences between fidelity, do we get the water in the right place, versus total model accuracy, which is very important for the soils and the evapotranspiration processes. And that's all I had.
Okay, thanks, Trish. That was fantastic. And the whole session was pretty much on time. We did well. Thanks for all of the speakers. I think that was a fantastic array of talks that showcased a lot of the work that we're doing in core modeling. I encourage everybody who is participating in the session to reach out to the authors over email if you've got any questions or want to have any further discussion. I would like to draw attention to the second core modeling session that we have tomorrow. It's parallel session 4 on improved tools for prediction of water futures. And that's being chaired by Al Petronero at the University of Calgary and Philippe Van Capellen from University of Waterloo. And it's under the conference theme, Innovations in Water Science and Technology. So I would like to thank everybody for your attendance and participation today. I really enjoyed all of the talks, and we look forward to seeing you throughout the virtual conference. Thanks very much.